In question 6, we have an arrangement to model radioactive decay. In 6.1, we're to determine the predicted depth of water at 57 seconds. Well, from the graph, you can see that the half-life, the time it takes for the water to go from 16 to 8 centimetres, is 19 seconds. So 57 seconds is 3 half-lives. Therefore, it would go to a depth of 16 over 2 to the power 3. Oops. Which is 16 over 8, or 2 centimetres. You could also do it by going time and depth. At 0, we have 16. After 19 seconds, we'd have 8. After 38 seconds, we'd have 4. And after 57 seconds, we'd have 2 centimetres. In 6.2, we're to suggest how the apparatus could be changed to show a radioactive sample of the same nuclide with a greater number of nuclei. Well, we could simply use more water at the start. In 6.3, we're to suggest how the apparatus could be changed to give a radioactive sample of a nuclide with a smaller decay constant. Well, a smaller decay constant gives a longer half-life, so we'd just reduce the flow by partially closing the tap. In 6.4, we're to calculate in years the half-life of rubidium-87. Well, half-life is given by the natural log of 2 over the decay constant. And the decay constant is in years, and we're after an answer in years, so this is fine. It's just ln 2 over 1.42 times 10 to the minus 11 years to the minus 1. And that gives 4.9 times 10 to the 10 years. In 6.5, we're told a sample of moon rock contains 1.23 milligrams, whereas to calculate the mass in grams that the rock sample would have contained when it was formed, we're to give our answer to an appropriate number of significant figures. Well, for this we can use activity is initial activity times e to the minus lambda t. I know we're after mass, but as the mass halves, the activity also halves. So we can equally use mass is equal to mass naught e to the minus lambda t. They'll both change in the same proportion. So we're after mass naught, which is mass over e to the minus lambda t, or is just mass times e to the lambda t. So the minus sign just means this is in the wrong side of the line. That is then 1.23 times 10 to the minus 3 times e to the 1.42 times 10 to the minus 11 times 4.47 times 10 to the 9. These are both in years, so that's fine to keep them in years. That gives a mass of 1.31 times 10 to the minus 3 kilograms, and we've got all our data to 3 significant figures, so we can give our answer as 1.31 milligrams. In 6.6, we're to calculate the activity of the sample with a mass of 1.23 milligrams. Well, initially we need the number, and the number will be our mass, 1.23 times 10 to the minus 6, over the mass of one atom, which is 87 times the atomic mass unit. Then, I'm not going to calculate this, I'm going to calculate it all together. We can use activity is decay constant times number. Now in this case, we need to have the decay constant in seconds. So that is going to be 1.42 times 10 to the minus 11, that's in years to the minus 1, If we then divide that by 365 1/4 to get it into days, 24 to get it into hours, 60 into minutes, 60 again into seconds, then we need to times it by n, which we've said is 1.23 times 10 to the minus 6 over 87 for the relative atomic mass, times the atomic mass unit, which is 1.661 times 10 to the minus 27 from the formula sheet. That gives 3.8, and the units are becquerels.